All right. Well, I'd like to thank the Fetzer Foundation and the organizers for this beautiful conference, which I was lucky to have come a few sequence. The topic you can see over there, we did not call it quantum equivalence principle. I want to explain that first because that might make people think that you need to come up with a quantum equivalence principle. So at least what we try to do here is to assume the validity of the equivalence principle, as we all know very well, for classical systems, and then explore the consequences of that for quantum systems. So it's this one. All right. This I could go very fast. Weak equivalent principle basically says that the inertial mass is equal to the gravitational mass at a very high degree of accuracy. The classical description, I would also classify it in two ways. If I may call it the Galilean one, which basically measures the rate or the time for different objects of different masses to fall the same distance. And you can see that, here, right? And then, of course, there's a sort of deeper implication in the way Einstein phrased it, which is gravity can be replaced, in quotes, by acceleration. So we usually say that the freely falling frame, the Einstein elevator, is the same as in physics. In the Einstein elevator is the same as in an inertial frame. Now, I want to say that even, some people might say, well, maybe we should go to quantum field theory in curved spacetime, even quantum gravity. We don't need to. It's already subsumed the equivalent principle in these theories, more sophisticated theories. For example, if you look at the wave equation in curved spacetime with a coupling of C to the curved spacetime with curvature scalar R, in the Laplace-Beltrami operator here, of course, it already contains the G, the metric, and the kinetic term there has the inertial mass, whereas the potential terms contain the gravitational mass. So it's already in there. And if you look at Einstein's equation, as we all know, it's both a field equation, in which case the gravitational mass enters, as well as an equation of motion, wherein, of course, the inertial mass enters. So with that preface, let's ask, what is different in a quantum world, right? It's quite different, right? The quantum description is in terms of state preparation, measurements, and probabilities. Whereas, of course, quantum states and processes, we distinguish pure state, mixed state, and tangled state, as well as, of course, the phasing versus the coherence. You see that those are actually quite different processes. It's not semantics. Sometimes when I tell people, they get tired discussing, and this is semantics. I'm sorry. We create words to carry real meanings. Okay, so that's just a forewarning. Now, how does the equivalent principle manifest in quantum physics? That's the question we pose. Well, quantum systems with internal degree of freedom, for example, atom, and external degree of freedom, like the center of mass, and that, of course, is what we use to have this notion of a trajectory. But the caution here is that as soon as you mention trajectory, you're no longer in the quantum world, because we should actually talk about quantum histories, and they interfere. So it requires quite a bit of qualification before you can even talk about trajectory, because it's basically a classical concept. All right? So we'll divide our studies in two parts. One is, we'll call it elementary particle, for lack of a better word. What that means is that there's no internal degree of freedom, okay? And versus an atom, for example, which is composite, And we study both of these objects in free fall. Okay? Right, so let me give you our finding, because I'm afraid I might run out of time if I start showing you the equations and all the details. I would again use what I just mentioned, the Einstein version, so to speak, is that the probability distribution of the position of a free falling particle is the same as the probability distribution of a free particle modulo a mass independent shift of its mean. The emphasis here really is the mass independence, right? That's what equivalent principle usually entails. And the shift of its mean really amounts to just the 1/2 GT squared term, right? So, and in the Galileo version is any two particles with the same velocity wave function. This is something I would expand on a little bit later. Behave identically in free fall, irrespective of their masses, right? This last part, of course, is what the equivalent principle that we are familiar with. All right, but then in quantum physics, we cannot just use mass as a representation, and we have to go to the velocity wave function to be precise, actually the velocity Wegner function. All right, so I'll just give you a little bit of the details. Probably you can't see too well, so I'll just highlight this for you. If you start out with the non-relativistic version, the Hamiltonian, of an object in a gravitational field. Here it is mgx, of course that's the potential term, this is the kinetic term, and the mass is multiplied by the identity matrix. You take the eigenstates, right, as energy, and certainly mass is equivalent to energy. And so in a gravitational field, you actually have both of these terms, and it's an easy several line calculation to say that, well, to evaluate it in the momentum representation, what is of interest, of course, is actually in the exponent here. And the generalized eigenstates are normalized, and then we define the propagator, right, from x prime to x, and from time 0 to t, that's what the subscript is, t. And then we will get the propagator, or the Green function. You can see the argument, really that's what we are after here. The superscript 0 in parentheses refers to zero gravity, and correspondingly this is the Green function in a gravitational field. And you see, of course, this characteristic x plus 1/2 GT squared, right? Okay, so now we get all the propagators. And then let's say that initially the state of the system is psi 0, sub-zero. There are too many zeros, so I have to sort of clarify that along the way. And then the subscript g, as I said, is the wave function, the state at time t, having evolved from t equals 0, subscript t, in the gravitational field, right? So now comparing these two sides, there's a 0 there without gravitational field and with gravitational field. You can see that, well, there's some algebra involved, which is the Weyl translation operator. We come up with the Einstein version quite readily, okay, which is, of course, is a probability that counts. And if you square both sides, you can actually see this argument there, which states that the probability distribution of position is the same as that of a free particle with the same initial state, but with a time-dependent shift of the center. The shift does not depend on the particle's mass, right? So this time-dependent shift is simply just the displacement there. The important part is really on neither side would the mass appear, quantum, okay? This is a quantum state. Now let's go on to the second version, the version B. So applies to, so before that, I should say a few things, the implications of that before we go to version B. That relation applies to particles prepared in any initial state, not only to particles prepared in a state with a direct classical analog. Okay, so this is important, right? If people care to carry out experiments later on, The result I just showed you actually applies to all these states, not necessarily requiring a classical analog. For example, coherent states, what's usually taken to be in that position. In particular, it also applies to cat state. Okay, gravitational decoherence, gravitational entanglement seem to be a hot topic these days. And if one day our experimentalist friend come up with a scheme, this would be of interest to see. Okay, it's also valid for composite particles. It remains unaffected by the coupling between internal and translational degree of freedom that's induced by free fall. The second part of the talk, the third part, we will analyze the situation where the particle has internal degrees of freedom, composite particles. All right? So, thus, the quantum test of EP could be used to constrain or discern different models of gravitational decoherence, which I just mentioned. Now, version B, the Galilean version, so to speak, we need to use the velocity Wigner function. Let me just say one thing about Wigner function. You can construct the Wigner function from the density matrix. It's pretty much a hybrid representation because the difference variable is the one that you Fourier transform, while keeping the sum divided by half variable center of mass variable in quotes, this depicting the overall evolution of the system itself. So, now, the important thing to state again, it was mentioned yesterday by Basso, is that the Wigner function contains the full information as in the wave function. Okay. Now, for the longest time, people attribute the Wigner function as a good description of the classical one-particle distribution function. That's true only for Gaussian systems. So harmonic oscillator, if you give that example, everything passes through. Okay. Now, so with that, we want to evaluate the Wigner function, that's the G now, right, of the system in a gravitational field at time t. For a particle mass of mass m freely falling in a gravitational field, and you carry that on the, let me skip over to this side, and then you see at the end that two particles of different masses, m1 and m2, but with the same velocity Wigner function behave exactly the same in free fall. All right? In the next slide, I'll explain to you why we have to use the velocity Wigner function and not the mass. But here, from that rather straightforward manipulation, you can actually come up with this result quite readily. Okay? So that's the equivalent principle for quantum system version B, which states that any two particles with the same velocity wave function behave identically in free fall, irrespective of their mass, or their masses. And why? Okay, why the velocity Wigner function? Well, in short, okay, so there's no correspondence between Hilbert spaces that correspond to particles of different masses. Okay, they belong to different representations, so you can't just compare the two. And so in fact, they are not unitarily equivalent representation. Whereas, however, if you take the Fall velocity, right, the only natural way of comparing the quantum state of particles with different masses is using the wave function defined with respect to the Fall velocity, because it is a unit Fall vector for all masses. Okay, that's the little thing that one needs to pay attention to. Let me now turn to composite particles, and it contains two parts. Okay. Composite particle, we refer to, of course, a particle with internal degree of freedom. And the two parts are that the internal degrees of freedom can dephase in the position basis. Okay? This is the internal acting on the translational degree of freedom. Okay? The second aspect is the effect of free fall, right, of the whole object on its internal degree of freedom. It shows up as gravitational phase shift. Right? So this part is actually probably more familiar to most people because there are quite a few famous experiments already carried out with atoms even, right? So just quickly, the internal degree of freedom, really, you need, of course, the interacting field theory, and the composite particles correspond to poles of the appropriate correlation function of the quantum field, right? So we label them, right, by n, these internal degrees of freedom, or even material particles, 0, 1, 2, 3, etc. And then you have to, of course, take the direct sum of the Hilbert space of each of these internal or the constituent particles, including mass and spin, and then you cross with the H0, the original, the whole particle, and the INT is not in can be written then, right, in this basis, which you can recognize. Actually, every element is like the first equation that I show you. Okay, so now you really have to take all these things together. And now the evolution of the Hamiltonian, I show you this V function without particularly pointing it out. That's basically a propagator, which enables you to go from which relates the case without the gravitational field to the case with the gravitational field. Now, what do we get there? Now, if we consider measurements only of the translational degree of freedom, so we need to coarse grain or sum over, it's not sum away, right? Sum over and come up with a reduced density matrix over the internal degrees of freedom, right? So now, if we see, if we look at this equation here, again, if you compare the two sides, really it's the argument that the state now, right, is changed with this x plus 1/2 gt squared. That's all, okay? One is, of course, in the gravitational field, the other is not in there. This is what embodies the version A of the equivalent principle for quantum systems. Now, in analogy with what we did for the version B or the Galileo one, that's all mass, particles of different masses for the same rate, right? So again, we have to use the velocity Wigner function, look for the reduced velocity Wigner function for the translation degree of freedom, okay? And then if you do a little bit of that, you see that, okay, so here it is. Let me slow down a little bit and show you that the dependence of this wave function on n, remember n marks the different states of the internal constituent or the degrees of freedom. This n, dependence of n, is not due to the initial condition, but due to the fact that there's a time evolution of the state is mass dependent, okay? So the mass dependence actually shows up in the n, and then what ends up here, you can see that there's a position dispersion, delta x squared, okay, between these two states as you let it free fall, and there we could see that it actually gives us first of all, it's a entangled state, the one that I just showed you, this 28 equation. And also, the density matrix for the translation degree of freedom is a mixed state, all right? There is a characteristic time here, I won't have that much time to talk about, but that's related to the dispersion that you observe. But the overall physics you can see is that the let me also skip over this part and come to the physics of it, right? This expression, 34, sorry, right there, that was what I was pointing at, okay, was obtained by Pekovsky a little bit earlier, but we disagree on two crucial statements. They call it universal gravitational decoherence. It's not universal in the sense that the result depends on the choice of initial conditions, okay? And more importantly, this is not decoherence because there's no loss of information. This is more similar to the spin echo experiment. If you wait long enough, you come back to it. There's no information lost to the environment or to anything whatsoever. And that you can actually trace through the derivation and see that clearly. I also want to point out that equation, the evolution is non-Markovian. That means that it has memory, And in fact, it has a memory of the initial state. It persists in time. So this is quite interesting, even with such a simple process, if it has internal degrees of freedom. And it depends on the specific choice of the initial conditions. So it's certainly not universal as such. The last part, let me say, Chairman, so when you say 5 minutes, is it 20 or up to 20 minutes? Or?
Yeah, 5 minutes for you and 5 minutes for the audience.
Okay, good. All right. I think I can finish in 5 minutes. All right, so the effect now, let's look at the other side, the effect of translational degree of freedom on the internal. So now the whole thing is falling. We want to study what goes on with the internal degrees of freedom, okay? And that shows up as gravitational phase shifts. And there are two parts to that. All right, so the phase shift from free fall, again, all right, so we consider factorized initial conditions so that we could do the reduced density matrix a little bit easier. And a localized initial state with the position spread, vanishing mean momentum, everything is set up that way. You can also see that it basically follows the classical description around the peak. What is interesting, of course, is the phase shift. So the qubit now, so if we assume for simplicity just two levels in the internal degree of freedom, and you can see the qubit density matrix has developed a phase due to the free fall. So now again, it is the free fall influence on the internal. So for atom, two-level atom, this should be an observable effect. Okay, it shows up as phase shift. And even though this has full quantum origin, the phi g actually, you can import associated classical interpretation. And what's interesting is that half originates from gravitational redshift, and the other half is from special relativistic time dilation. Sometimes in elementary courses, people say, oh, come on, all the gravity, we don't need general relativity. You can just describe it in terms of special relativistic effects. It's not actually that. It's not true, okay? In this case, actually, both actually enter. And I'll spare you with this, I guess, right? This is basically take a Schwarzschild space-time, have a radial info of the particle, look at the G0 component, expand it in time. And then the leading term, we can get it in the next slide. There is a time delay, which amounts to, of course, a phase shift of the qubit of frequency omega. So this is measurable, and we plug in some numbers here, and some of our colleagues reminded, well, in fact, as I mentioned, I think quite early on, several decades ago, people have been observing these gravitational redshift effects. So it would be interesting to either look up those literature and see how much of that really comes out matching the quantum description here. Right? So I can see the chairman staring at me. Let me summarize. The first is again a repeat of this statement. The probability distribution of position for a free-falling particle is the same as the probability distribution of a free particle, modulo a mass independent shift of its mean. And the second one, the Galileo one, is any two particles with the same velocity wave function behave identically in free fall, irrespective of their masses. Second point, the coupling between internal degree of freedom and the translational degree of freedom is that the free fall induces a coupling between the internal and the translational degree of freedom. It depends on the initial state of the system. And for a particular class of initial states, we show that the internal degree of freedom can lead to a suppression of the off-diagonal terms of the density matrix in the position basis, which of course is dephasing. Okay, not decoherence, is not universal, is not decoherence. And lastly, we found a gravitational phase shift in the reduced density matrix of the internal degree of freedom. And while this phase shift is a fully quantum effect, it has a natural classical interpretation in terms of gravitational redshift and special relativistic time dilation. Thank you for your attention.